Now we will consider the power and energy in a capacitor. As usual, we take the voltage and current I with the appropriate passive sign convention. Then the power, just like for any two-terminal element, is the product of voltage and current. But of course, the characteristic of a capacitor is that it enforces this relationship I equals C times the time derivative of voltage between the current and voltage. Okay. Now, of course, we have to substitute this current into this expression to give us C times V of t times dV dt. Okay. Now, first of all, this expression looks a little more complicated than that for a resistor, but the important point here is that this is the power delivered to the capacitor, and this can be either positive or negative. Okay. Because let's consider some voltage waveform, and the voltage could change in this way versus time. Clearly here the voltage is positive and its derivative is positive. Okay, it means that there is a positive voltage here. On the upper plate there is positive charge, and that is increasing with time. So current has to flow in the upper terminal. Okay, so the current is also positive. So clearly this product here is positive and the capacitor is absorbing power. Now the other way around is also possible. Let's imagine that the voltage does that, where the voltage is positive but its time derivative is negative. Here this product will be negative and the capacitor will be delivering power. Okay, it is absorbing negative power. Okay, then we continue on that way, where V is negative and the time derivative is also negative. So the product is positive, and in this case again the capacitor is absorbing power. And finally we can do that where V is negative, whereas the derivative is positive because the voltage is increasing and the capacitor is delivering power. Okay, so this is possible because depending on the voltage value and its rate of change, we can have the capacitor to be either absorbing or delivering power. So here it absorbs power, here it delivers power, and here again where I have shown the green part of the waveform, it absorbs power, and in this part it delivers power. Okay, so all these things are possible. Now if the power delivered to the capacitor can both be positive and negative, how do you tell if the capacitor is a passive element or not? Okay, for that we consider the energy delivered to the capacitor. This of course is the integral of P, which is integral of V I dt. Okay. And let's imagine that the voltage across the capacitor changes from 0 to some value Vc in a time from 0 to t1. Okay, so the horizontal axis is the time axis, and we want to find the power delivered to the capacitor in this interval 0 to t1. So we have to carry out this integral from 0 to t1. Okay, so this is nothing but 0 to t1 C times V, time derivative of V with respect to time. Okay. Now this looks very complicated. V itself has some kind of variation. We have not specified what that is. Its time derivative looks complicated. And then finally, the integral of that, how do we evaluate it? But it turns out it's very simple and it doesn't depend on any of the details of this waveform. You realize that this V times time derivative of V is nothing but it's something related to the time derivative of V square. Okay, the time derivative of V square is 2V time derivative of V. Okay, so this part is half of time derivative of V square. So basically the energy delivered to the capacitor is nothing but C divided by 2 from here times the time integral of the time derivative of V square. Okay, we have the time derivative of V square and we integrate it with respect to time. So obviously we just get this function itself, V square, over the appropriate limits from 0 to t1. So which means that the voltage goes from over a time interval 0 to t1, the voltage goes from 0 to Vc. And this gives us finally the expression for energy delivered to the capacitor over this interval, which is half C Vc squared. Okay. So if you have a capacitor starting from 0 volts and you change its voltage from 0 to a voltage Vc in some way, it doesn't matter what waveform is used, the total energy delivered to the capacitor is half C Vc square. Okay. Of course, this gives you the formula for the capacitor's energy when its voltage is Vc, because if the capacitor's voltage is Vc, you can imagine that it is taken from 0 to Vc in some way. It doesn't matter how you take it. Okay. So if you do that, you have delivered an energy of half CVc square to the capacitor, and this energy half CVc square will be stored in the capacitor, because if you now take it back to 0, okay, what I just showed you, this energy is the energy in the capacitor over here. Okay, let's say after that the capacitor voltage goes to 0, okay, like this, and we know that in this interval when the voltage is positive and the time derivative is negative, it delivers power. But also we know that basically the energy here will again be 0. Okay, it starts with 0 energy and it goes to half CVc square and it comes down to 0. So this energy that you delivered, this half CVc square, doesn't go anywhere. Okay, so during the charging process you delivered energy to the capacitor, and during the discharging process, as the voltage falls from Vc to 0, you can recover all of that energy. It delivers that much energy. Okay, so a capacitor stores energy, unlike a resistor which dissipates the energy that is delivered to it. But the one thing is that the net energy delivered to the capacitor is always positive. That is, you assume that a capacitor starts from 0 volts, it has 0 energy, and then after that you change the voltage in whatever way you want and take it to some voltage Vc. The energy delivered to it will be half CVc square. Because of the square term, the energy, this quantity will be positive, so that means that a positive energy is delivered to the capacitor. Okay, so once a capacitor is charged to some voltage, you can have the capacitor deliver the energy to the rest of the circuit. But starting from 0 volts, the capacitor always absorbs energy. A capacitor is also a passive element. So like I said, you can charge it to a certain voltage Vc and then have the capacitor deliver energy to the rest of the circuit, or basically capacitor absorbs negative energy. But to get to the starting point where it is charged to Vc, you had to supply energy. So if you take the net energy absorbed by the capacitor, it will be positive. Okay. So capacitor absorbs energy and it is passive. Okay. Of course, this is a useful application of a capacitor. You can charge it to a certain voltage and use it as a source of energy. Okay. So that's what a capacitor is used for in many applications. So the summary is that capacitor absorbs energy, and also a capacitor at a voltage Vc, that is, when a capacitor has a voltage Vc, it has an energy stored in it, which is half C Vc square. Okay. This clear? Now let's take a quick numerical example. I have a capacitor C with a voltage V and a current I. Let me define the capacitor voltage waveform. Let's say it is 0 for t less than 0. Then it rises to 5 volts over an interval of 10 microseconds, and I assume that it will increase in a straight line, and then it stays constant at 5 volts. And let's say the capacitor value is 10 nanofarads. Now I'll plot the current through the capacitor. We know that before t equal to 0, the voltage is constant, so the current is 0, and above t equals 10 microsecond, the voltage is again constant, so the current is again 0. But between these two intervals, the current, which is C dV dt, is 10 nanofarad times 5 volts divided by 10 microseconds will be 5 milliamp. So over this interval, because I assumed a straight line variation in voltage, we have a constant current of 5 milliamps, otherwise it is 0. Now what can we calculate from this? First of all, we can calculate the power, which is nothing but the product of voltage and current. Okay. So before t equals 0, both voltage and current are 0, so the power is 0. And after t equals 10 microseconds, the voltage is 5 volts, the current is 0, so the power is again 0. And in between these intervals, we have a straight line like this multiplied by a constant. So this is a similar straight line. Okay. And the value it reaches here at t equal to 10 microsecond is the product of this value 5 volts and this value 5 milliamps. So this is 25 milliwatts. Okay, this is 5 milliamp times 5 volts. So this is how the power in the capacitor, power absorbed in the capacitor changes with time. Now, what is the energy stored in the capacitor? The energy stored in the capacitor at any point can be obtained by integrating the power curve up to that point. So let's say we take this particular point, then we have to compute this area. Of course, we don't have to do it like this, because we already know that if the capacitor voltage is a certain value Vc, the energy stored in it will be half C Vc square. We started from 0 volts, it goes to Vc, so the energy absorbed by the capacitor is also the same thing. Okay. So the energy absorbed up to this point, t equals 10 microsecond, or equivalently the energy stored at t equals 10 microsecond is half C Vc square, where I have to take the value of the capacitor voltage at 10 microsecond is half 10 nanofarad 5 volt square. Basically we are looking at this point here, which is 125 nanojoules. Of course, if you take the trouble to integrate this curve, you will find exactly the same value. Okay. So the reason I showed it is, first of all, just as an example, calculation involving power and energy in capacitors. Now the energy is very easy. You know the voltage across the capacitor, you know the energy stored in the capacitor. It's perhaps less usual to calculate the power in a capacitor, but it can be done as I showed here. And the other reason I showed this is also that I find many students are not very comfortable with drawing waveforms, or they are not used to it. But I personally find that drawing waveforms are a very good way of getting intuition about circuits. They are not for precise calculations. For that you use the calculator or the computer. But to get a sense of which way things are varying, it's very good to draw the waveforms. And the kind of example I solved here, and also the kind of problems that are in the assignments, where the waveforms are piecewise linear, it's very easy to do. Okay. So I strongly encourage you to draw the waveforms, at least for some cases, to get an idea of what is going on in the circuit. Okay. So especially things like capacitors, where the time derivative enters the picture, you may not always be able to calculate things exactly, but you can get a sense of variations by sketching V and the time derivative of V and so on. Okay.